here I rewrote the initial integral in terms of this sum over the residues, which is here, as you may notice, and 1 over I, this prefactor which we figured out on our previous slide. And now let's simplify this expression slightly so it takes a more suitable form. Well, first of all, let's split this sum into their two sums over odd and integer n, and as a result we get the following thing. We can factor out two prefactors here and here, and what we get is the combination of the two very suitable sums which we just encountered when we discussed the properties of their digamma function. Namely, the first sum is just 1 over k plus 1/4. As you remember, there is the following property expression for their Euler's digamma function. Namely, it can be expressed as the sum from 0 to plus infinity of the following difference of two expressions: 1 over k plus 1 minus 1 over z plus k minus gamma. Oh, just a second, probably plus gamma. Oh, no, minus gamma. Right. And here we just see precisely very similar combination. Namely, there is this k plus, so this is going to be z in one case and z in another case. So what we see here is basically the difference of two digamma function. Indeed, because we can subtract here the suitable 1 over k plus 1 term and reduce the first term to the psi function of this argument, and we can we can add the same combination to group it with a second sum and to end up with the digamma function of the second argument. And naturally, now our integral, or rather the derivative of the integral with respect to a, is reduced to the difference of two digamma functions. The first one is psi of 3/4 minus ia over 2 pi, and the second one is the same digamma function is the change 3/4 is changed to 1/4, 1/4. Right, so now it's a partial success because we compute the integral, but it's a derivative. So in order to restore the original integral, we need to integrate the left-hand side and the right-hand side of our equation. So when doing so, it's the key point is that to recall the definition of the digamma function. Digamma function is a log derivative of the Euler gamma function. So it's very easy to integrate. As a result, we integrate both parts of the equation. And here we get the difference of two logs of the Euler's gamma function. And here we add an additional prefactor, which comes from the antiderivative, which is 2 pi divided by negative I. So it's basically times 2 pi I. So hence I disappears completely. However, there is a problem because we take an indefinite integral from both parts. So there is additional a independent constant here, which we should somehow fix if we want to compute the whole expression exactly. So how do we fix this integration constant? Since it's a independent, it stays the same even if we take a tending to plus infinity. Why would we don't do this? Because it's a tending to plus infinity, the expression for gamma functions are simplified due to this standard Stirling asymptotics. And yet the original integral, which is a dependent, is also simplified. So let's write down again the expression for the original integral I1. I1 was defined as the log of x plus a divided by the corresponding cosine hyperbolic of x. It's easy to see that the convergence, the important regions of convergence of this integral are the x, so they're defined by the behavior of the denominator, because the denominator contains exponential functions, and exponential functions are they decay, or on the contrary rise, for x of the order of 1. So the important regions of the integration for this integral, where the integral accumulates its value, are from x in the segment from -1 to 1. So if a tends to plus infinity and important x are of the order of 1, we can discard this x in the first approximation. We can discard this x when taking the integral. So if a tends to infinity, then the first expression in our asymptotic expansion would look like logarithm of a times the integral of a simple cosine hyperbolic function. And we encountered in this integral before, and it's very easy to compute. And the answer is pi by 2. So here's our expression for the integral for large A. On the other hand, we can extract the correct expression for the integral using this gamma function expression. And fortunately for us, there is this very nice difference of 2 logs asymptotic expressions, and which can be reduced to the ratio of 2 gamma functions. And we simply use their Stirling formulas for each of them. And you can check it yourself, but I'll just give you the answer for this difference for large A, just trivial algebra. And the answer is as follows. So the answer is 1/4 times the logarithm of a squared over 2 pi squared minus pi I. So that's the difference of these 2 logs. So some special care should be taken about the regular branch of the corresponding asymptotics. As you remember, the asymptotics of the gamma function is defined in the segment of the complex plane with excluded negative real axis, because there it has a branch cut, because the asymptotic contains the log functions. So when we treat these large IA arguments, we can see that this negative I, we treat this negative I complex number as e2 minus I pi by 2. And as a result, if you follow every step correctly and accurately, you will recover this minus pi I factor. Just check it yourself. So, and now we just plugging this asymptotic into our I1 expression and recover basically the correct value for our C constant, right? And as a result, the constant, let me write it somewhere above. The constant C is, just for reference, it's pi squared I by 2 plus pi logarithm of 2 pi. We are basically almost there, so now we are ready to get the original answer for our I integral. So let's make this final step. And finally, here is the expression for our I1 auxiliary integral with the constant C restored. And now our last step is to compute this integral, to basically to plug in a equals 0 to the integral. So I1 of 0 is, of course, sorry, here is 0 here. I1 of 0 is simply 2 pi logarithm of gamma function of 3/4 divided by the gamma function of 1/4 plus this additional imaginary constant. And while this expression should be equal to the original integral, which is just 2i plus pi squared I over 2. And as we see, this imaginary part is cancelled. And we recover the expression for the original integral. And one last step, what you should do, you should, to get the answer, you just use the mirror formula for the Euler gamma function. Right, so, and once you collect all these pieces and plug it into your original, to the log, you recover this quite astounding expression for this original integral. So I hope you understand now, and you've seen the power of this special function representation for this 1 over z plus a sums, and how they can be expressed via Euler's digamma function, and how just with simple tricks we can get exact answers for highly non-trivial integrals.